Welcome to the course Mastering CFD using SolidWorks Pro Solution. Whether you are a beginner or intermediate learner, you must gain sufficient knowledge and confidence from this course. In this video, I'll discuss the basic principles of computational fluid dynamics. Together with the course content, it will be a brief introduction to CFD. Now, the first question comes to our mind: what does computational fluid dynamics mean? This means that in contrast to real flows, the flows can be calculated using computers. In a different way, we can say that we can find pressure, velocity, temperature distribution, and a lot more engineering parameters with the simulation on computers. Like FEM, in CFD processes also we are having three main steps. It is pre-processing, processing, and post-processing. In pre-processing, we have to model the object, and then we need to apply proper boundary conditions. And modeling involves the continuous mathematical functions that we use to describe the real flow. But in reality, that flow is the consequence of the different laws of physics working together, all having their impact on the flow to limit computational effort. To avoid modeling errors, it is important to select the correct and all the relevant physical models. The most important model for fluid dynamics is a set of partial differential equations called the Navier-Stokes equations. These basically describe and apply the laws of Newton to every small bit of fluid within the flow field, stating the dynamic balance between the forces acting on the small bit and the change in its momentum. This conservation of momentum together with the conservation of mass allows us to describe a flow field. There are analytical solutions. The entire flow field can also be described using continuous mathematical functions. This allows us to calculate the pressure and velocity at any given point within the flow field at an infinite resolution. But for more complex cases, we don't have any analytical solutions. This means that we need to break the reality into small blocks for which we do have a solution depending on the method. This can be a finite element method or a finite volume method. Here comes the term discretization. This process of breaking down a large continuous flow field into small cells is called meshes. For each of these elements of cells, we can approximate the continuous Navier-Stokes equations with discrete algebraic ones. This allows us to calculate the pressure and velocity at the center of each element or cell, also called node, based on the pressure and velocity values of the surrounding nodes. The higher the order of these discrete approximations, the more the surrounding nodes are included. This reach of a single node is called the computational molecule, resulting in a set of algebraic equations for each node, as the value of one node depends on the value of the surrounding nodes and vice versa. These equations are connected, and to solve them we need to put them all together into one big matrix. Like finite element method, we're trying to reach towards the theoretical or perfect results, and the accuracy of the results depend on the degree of discretization. And the difference between the simulation results and the exact solution of governing equations is known as discretization error. To have an accurate results, we need to focus on better meshing quality, because we know that better the mesh, better is the solution. To minimize the discretization error, we need to go on meshing and remeshing again and again till we reach the minimum error. When we get the exact solution, then we can say that convergence criteria is achieved. Once we have defined our mesh and matrices with all the equations, we can solve them very easily. We can obtain the exact solution through a direct method like Gauss elimination or LU decomposition. We know that LU decomposition method is faster than Gauss elimination method, but sometimes it is impossible to write a matrix in the LU format, which is better known as lower triangular and upper triangular matrix. But this is a very complex one, so we need to solve these equations using computer with high level of accuracy. This is where the faster iterative method comes in, and in this method they start by guessing an initial approximate solution. The longer we iterate, the more we converge to a stable flow field and the more we reduce the iteration errors. The difference between this solution and the direct solution of the equation is called iteration error. So, to obtain an accurate computational fluid dynamics results, there are three different types of errors we need to keep under control. The first one is the modeling error, which is the difference between the real physics and the actual models. The second one is the discretization error, introduced by chopping up reality and then approximating them into continuous equations with discrete ones. And thirdly, there is an iteration error, which is the difference between the exact solution of the equations and that one obtained via iteration. Now let me talk about the importance of CFD. Whenever we want to go for new product development or technical project or research, we need to go for different types of analysis, and finally we get our results. But we are not confident enough whether our solution is right or not. That's why we need to validate our results with experimental findings, and that should be supported with theoretical as well as results from software. But experimentation is not always possible because of some issues. The issue may be from economic point of view or maybe from feasibility point of view. In those cases, software validation gets high importance for the project. If we talk about software validation, CFD or computational fluid dynamics is one of the best tools because of its versatility and wide range acceptability. It has a wide range of applications. It can be applied in different fields like aerospace, automotive industry, biomedical field, chemical and processing industry, HVAC and refrigeration industry, hydraulics, marine engineering, oil and gas field, power generation industries, and even in sports also. You can solve any complex engineering problem with the knowledge of CFD. There are two reasons to take this course. Number one, assurance to have enough confidence and knowledge of CFD to this course even if you are a beginner. Number two, with your proficiency, you can boost your career as a CFD professional. The main aim of this course is to strengthen your conception and to boost your confidence to solve any real-world engineering problem with CFD. This is a professional course made with lucid explanation and utter care, especially keeping in mind of the beginners. There are 21 videos in this course covering almost all the CFD techniques, which one you can apply to your projects. This course is divided into 5 different segments or 5 different units. Unit 1 contains 9 videos with internal fluid flow analysis and optimization. Unit 2 contains 3 videos with flow through turbo machines and optimization. Unit 3 contains 3 videos with multi-phase fluid flow analysis. Unit 4 contains 4 videos with thermal management. And finally, Unit 5 contains 2 videos with aerodynamics. I hope you will be enjoying these videos and I am looking forward to see your comments. Thanks in advance for watching these videos. See you soon.